This is Alex. He's applying for a loan. Now, if you or I were looking at his credit score and income, the decision might feel pretty straightforward. But here's the crazy part. A neural network can do this too, by turning those numbers into its own kind of reasoning process. And if I asked you to sit down and write a program that takes in credit score and income, and then outputs a yes or no loan decision, it suddenly feels a lot less obvious. That's where neural networks come in. What I want to show you here is how a neural network actually works, not as a buzzword, but as a concrete step-by-step process. And my hope is that by the end, you'll see how the structure makes sense and how all the little pieces fit together. Here's the setup. We'll give the network two inputs, credit score and income. For Alex, that's a credit score of 80 and an income of 60,000, which we will just represent as 60. The goal: output yes if he should get a loan, no if he shouldn't. Simple idea, but let's see how a neural network turns those two numbers into a decision. As the name suggests, neural networks are inspired by the brain. But let's break that down. When I say neuron here, I just mean a little calculator that takes in numbers and spits out another number. That's it. In our example, our network has three layers. First, the input layer. Two neurons holding Alex's credit score and income. In between is a hidden layer of three neurons. Each neuron composed of an activation function and a bias. More on that later. Think of this as where the learning process happens. And lastly, the output layer. One neuron taking in all the information our network learned and giving us a yes or no. Now let's actually walk through our neural network step by step. This process is called the forward pass. We're going to send Alex's data through the network and see what decision it makes and why. First, let's start with our inputs. Remember, Alex has a credit score of 80 and an income of 60, since we're using thousands. These two inputs get passed into the hidden layer. Each input connects to all three neurons in that hidden layer, giving us 6 total connections. Every connection has something called a weight attached to it. Think of a weight as a measure of importance. The higher the weight, the more influence that input has on the neuron's output. Here, we already predefined weights for our connections. Each neuron takes its inputs, multiplies them by their respective weights, and adds them up. We also tack on a little extra number called the bias. You can think of the bias like the neuron's built-in hunch or baseline opinion before it even looks at the data. In our case, a negative bias means the neuron leans towards not giving a loan, while a positive bias means it leans toward approving one. Finally, the neuron runs the total through an activation function. Activation functions add non-linearity, which basically means the model can handle messy, real-world patterns. Think of this like a filter. It decides whether the neuron signal should go through, and if so, how strong. In our case, we're using ReLU activation function. If a number is positive, we keep it. If it's negative, we drop it to 0. Simple, but super effective. Let's open up our hidden layer's first neuron, H1, and see what it's doing. Okay, so we can see our first weight of 0.3 in red. Our second weight connection is 0.5 and is in purple. Now we have to multiply each input by their own respective weight. We then add the results, and on top of that we have to add our bias. In our example, we have to multiply 60 by 0.3 and 80 by 0.5. We then add that up and then add our bias of 1. Now we apply the ReLU activation function. It's simple. If the number is positive, keep it. If it's negative, make it 0. 59 is positive, so H1's final output is 59. We repeat this for the other hidden neurons. H2 gives us 38, H3 gives us 44. Great, now our output neuron, the boss, has to make sense of these three opinions. It works the same way. Multiply each hidden neuron's output by its weight, add them up with a bias, and then run it through an activation function. That's a pretty big number, but we need to convert it into a clean yes or no. To do that, we use the Sigmoid function. It squashes any number into a value between 0 and 1. Basically a probability. A value of 56.9 gets squashed to almost 1, meaning the model predicts yes with near certainty. And since Alex's correct label was yes, the model got it right this time. And that's it. That's the core of how a neural network works. We took data, pushed it through a network of simple calculators, and got a decision. The intelligence isn't in any single neuron. It's in the complex patterns of all the weights and biases learned from the massive amounts of data. This was a tiny example, but the same exact principle powers the AI in your phone, your social media feeds, and even self-driving cars. If this clicked for you, do me a huge favor. Hit that like button, subscribe for more videos, and let me know in the comments what other AI concept we should break down for the next. Thanks for watching, and I'll see you in the next one.